Welcome to yet another exciting episode of How the Body Works, an educational series as a part of McMaster's Demystifying Medicine. I'm Matt.
And I'm Susie.
And today we'll be focusing on carbon dioxide and the chemical role it plays in our bodies to keep us alive. Have you ever wondered why a person would suffocate if he or she is deprived of oxygen and exposed to a large amount of carbon dioxide? Well, you will by the end of this video.
So for today's agenda, we will be talking about the influence of carbon dioxide, the clinical disorders of acid-base homeostasis, and a recap of the presented information.
Did you know that a person suffering from diabetes has acidic urine and a higher breathing rate than a normal person? Why is that? Not surprisingly, you are not the first person to wonder. Since the latter half of the 19th century, many researchers have tried to find the reason behind this phenomenon. One of these researchers was Friedrich Walter, who gave dilute hydrochloric acid to a non-human mammal and observed that his breathing rate increased.
The search for the answer didn't end here. With progression in the field of chemistry came new knowledge. In 1907, researcher Lawrence Henderson became the first person to place the role of carbon dioxide on a theoretical basis, thereby modifying the law of mass action, as described in the previous video. He described the role of carbon dioxide as shown below. Carbon dioxide in water makes carbonic acid, which dissociates into protons and bicarbonate. From this discovery, Henderson was instrumental in establishing the Henderson's equation, which helped measure the acidity of a solution as shown below. The concentration of protons in a solution is equal to K, a unitless constant multiplied by the ratio of weak acids to its conjugate.
Henderson later modified his equation to this, as he knew that the concentration of carbonic acid depends on the pressure of carbon dioxide. This equation is not only important mathematically, but also conceptually, as it relates the acidity of the solution to the level of carbon dioxide. In this equation, the concentration of protons is equal to K, again, another unitless value, multiplied by the ratio of the pressure of carbon dioxide to the concentration of bicarbonate. Thus, if pressurized carbon dioxide is halved, the acidity of the solution will increase unless the concentration of bicarbonate is lowered. It must be remembered that this relationship is in equilibrium, so the reaction can go in either direction. Both the arteries and veins help maintain this equilibrium by carrying and removing oxygen and carbon dioxide respectively. This helps maintain homeostasis.
Ever wonder how homeostasis is examined in our body? It's actually quite simple. In any routine clinical practice, there are three components in our blood plasma that are used to measure our body's homeostasis. 1. The total concentration of ions from strong acids like sodium and chloride, which are the two most important ions in our blood plasma. 2. The total concentration of weak acids, which, as mentioned in our previous episode of How the Body Works, are the amino acids, protein molecules of the hemoglobin, and phosphates. And lastly, 3. Carbon dioxide, which is often calculated using the concentration of bicarbonate. When all three criteria are met, homeostasis is achieved and all is good to go. However, in the unfortunate case when homeostasis is not achieved, clinical disorders may result. These disorders are commonly known as the following: respiratory acidosis and alkalosis, named after the decrease and increase of the physiological pH of 7.4 respectively due to the imbalance in the concentration of bicarbonate, and metabolic acidosis and alkalosis, known for the decrease and increase of pH respectively due to the imbalance in the concentration of strong ions and weak acids.
However, things are not as simple as defining disorders by the irregularities in pH in the body. As you might have already imagined, the body likes consistency, and has many ways to adjust for the imbalance of pH. This is referred to as adaptive responses. Let's consider hyperventilation, for example. When a person hyperventilates, there is an increase in the partial pressure of carbon dioxide in the body, which results in respiratory acidosis. To compensate, that individual would excrete chloride in one's urine to cause an increase in strong ion difference. This change in ion concentrations causes an increase in bicarbonate in the bloodstream, which can be defined as metabolic alkalosis. As you can see, while acidosis and alkalosis can be defined by a change in pH, there are, in fact, many other physiological and metabolic changes taking place in the body that characterize this change. Also, there are modifications that subsequently occur to lessen the severity of the imbalance. Many major illnesses in the body result in these changes in acid-base homeostasis, and each variable has to be carefully treated so the body can return to normal.
To conclude, there are three mechanisms to control blood pH: the carbon dioxide pressure system, balance of strong ions, and plasma proteins. It is safe to say that the carbon dioxide pressure system is remarkable for its ability to change rapidly with breathing. Hence, it's a rapid contributor to the control of homeostasis in our blood. But hold on, didn't we mention something regarding strong ions and essential plasma proteins in our previous video? Where did they go? Fortunately, the kidneys also play a vital role in homeostasis. However, in comparison with the carbon dioxide system, the rate of control for the concentration of strong ions and plasma proteins depend on the excretory function of the kidneys, which could take several hours. Therefore, keeping a constant pressure of carbon dioxide in our blood is highly crucial for our survival. But at the same time, we must appreciate the beauty of carbon dioxide and how it makes our sodas taste so good.
Well, that's all we have for today, folks. Thank you guys for listening, and we hope you enjoyed today's episode of How the Body Works. Feel free to click, follow, and subscribe. Check us out on Facebook, or visit our website at www.demystifyingmedicine.ca. See ya!
Bye, guys!